We commonly write it as forces mass into acceleration. Then this is the Gauss law for magnetism, Faraday induction, Ampere circuital. Now I have written these equations over here, but these equations are something very, very fundamental. Why I'm saying that they're fundamental? Because in a way they're describing how physics works. This first equation here almost describes all of what we call as classical mechanics. I mean, I'll not say all of, but most of it. And these other four equations, they define everything in electromagnetism. These are what we call as Maxwell's equations. But what are they actually doing? So I just want to ponder on that for a few moments. So these equations, they are actually trying to tell us that if we are making a mathematical model of a universe, then how we describe that universe. So these are some formulas which hold true in that universe. And specifically these equations, these are actually fundamental in our model of the universe, because we say that these equations have to hold no matter what sort of a model for the universe you come up with. So these are some fundamental parameters in this universe, and physics, as we try to describe it, is a description and refinement of the system. Okay, so keep in mind that throughout this whole talk we'll keep on getting more precise and better definitions for physics and this universe. So we are basically trying to refine the system. And so here's a fun fact: the more precisely we know the system, the more precisely we'll be able to predict things in the system. Because as we know, science is not something which is just, you see something and you can just say, yes, this would happen like this. You have to give a description. But just knowing something and repeatedly getting an answer doesn't mean that that's science. You should be able to predict things. That is the most important part about science. It is not understanding, it's prediction. Okay, so that is what we want from a system over here. And what we are saying as the universe, it is all the space and time and everything which is including, everything which is contained there, including all forms of matter and energy. So what is matter and energy? I would not go into that right now, but I suppose most of you have an idea about that. Space and time, these are also words which I'm just using vaguely over here. See, there are many words which I'll be using vaguely, which I suppose most of you have heard before. Because to define any of them precisely would be another webinar or something like that. Okay, so the current view that we have of a universe is something that took humanity a long time. And this whole talk would be a journey all throughout that time. And it took us a long time to come over here. So I suppose most of you are in your college years, so most of you are born in something around the 1990s till 2000s, right? So I'm from that generation which was born while looking up at photos of Kalpana Chawla, of Rakesh Sharma, and then looking at the various galaxies, looking at the photo of Andromeda and feeling like, wow, the universe is so big. There's a galaxy, there's stars, there are planets. Okay, but now think of it like this: that this sort of a thing happened very, very recently. Just the generation after us, someone who's born in, let's say, 2010 or something like that, they would actually be growing up while looking at photos of the black hole. Now, when I was a kid, the one thing I knew about a black hole is that it's so dark. It is such a thing in the universe that no light can escape from it. So if anyone would have asked me, can you actually see a black hole? Can you have a photograph of the black hole? I'd be like, are you trying to just bluff with me or something? That's what a joke are you saying? But right now we have actually got pictures of a black hole. Not exactly a black hole. Technically, we have gotten a picture of what we call as the accretion disk. Still, that was a major thing which happened just last year. So things are changing. With the evolution of technology, we are actually getting better and better understanding of our universe. But the key idea that you have to understand over here is that this is the physics, this is the understanding of physics that we have right now. And our understanding of the universe comes with our understanding of physics. They are completely correlated. But whenever I'm in this talk, try to just imagine that if you were someone who was living in that sort of a timeline, could you have had that sort of a thought or that sort of an idea? Okay, so just keep it at mind that keep your biases that science has given you aside and think of all of this from an unbiased point of view towards how a person, let's say, who's living in the 1st century BC might have actually thought of the universe as. Okay, so now that we are done with the philosophy, we can actually start the actual talk. Okay, so again, good evening to all of you. So the first ideas of the universe start with the timeline when man actually became a prominent species on Earth. So I'm talking about early man. This is something like 2000 BC, something like 20,000 years back from now. So at that time, there was nothing. I mean, there was no civilization. There was just some men who were actually cave dwellers. They had access to primitive tools. There was no metal. There was nothing. They just knew how to hunt and gather. But now, from that point of view, imagine that if there's someone who actually has got his nice own cave, okay, he's got some beast skin on his body, he actually has access to water, he has some food, he's eating, and then one day he's actually just sitting down and the sun's gone down and he's looking at the sky, and then he's wondering, you know, is this yellow ball which is out there in the sky just for me? I mean, there's this yellow ball which comes up every time. It is giving me this fuzzy, warm feeling. Then it goes down every day. Then there's this whitish, silvery ball which is out there, which is coming. Sometimes it grows big, sometimes it grows small. And then when everything is down, I can see all these twinkling gem-like objects in the sky. Are they put there only for me? I mean, is this just for me to look at and enjoy? Or is there a deeper purpose? I'm not saying everyone would have thought of that, but there might have been some crazy genius who might have thought of that. Maybe there's something more to this. And that would have been the advent of what we call as the beginning of astronomy. Someone is just looking at the night sky and trying to figure out, is there some sort of an order in this heavenly chaos? What is out there? What am I seeing? Does it make sense? I mean, why are they actually going about every day? That was the first question which people asked. And that is where things started changing. So this was the beginning of civilizations and settlements. And this is what we have read in history, that, well, how it is that these things are going about the way they are. I mean, civilizations, when they came into being, that was when we firstly started to look at the night sky properly. So I have a quick question. When do you think have been the first astronomical evidences being found? I mean, people doing astronomy, which is the oldest known, well, I should say oldest found relic, which tells us that people had studied astronomy. So you might have heard that early man used to draw in their caves and then of beast skins and things like that. So the earliest known things that we have heard of is people documenting solar eclipses and lunar eclipses in 15,000 BC. That is 17,000 years before today. And even at that time, people were thinking that this is all there just for me. Maybe they took it for granted. Maybe they didn't. And this is where the story starts. So now, once the civilization starts, people actually start going away from what we call as a nomadic life, a life of hunters and gatherers, to an agrarian life, where they have got a well-settled society. They are now plowing on their fields. They have got crops. They have got access to lots of resources. Now they are not actually running away to just save their life. They have got a place to call their homes, and they can actually look at things. But this one thing which every historian would tell you is that whenever a civilization comes into power, it actually has to come in power along with the existence of a calendar. So why a calendar? Because a calendar would allow you to keep track of everything out there. So at that time, what was everything? Well, you have to plant crops, you have to reap crops, you have to look after your herds, you have to see that you're putting crops in a proper place before it rains, so that they don't just become bad. So how do you keep track of it? So people realize that there's a periodicity. There's a periodicity of day and night. There's a periodicity of all these seasons. And what was important for them was the seasons. But now the only periodicity that they understood was of day and night. So how to actually understand day and night and these periods? So I suppose at that time there might have been someone who would have tried to figure out that, maybe there's some pattern. Maybe there's some pattern which is going to tell us how exactly this is happening. So this was the first time when people might have realized that approximately 12 times after a full moon, the season repeats. Approximately 12. So a lunar month, that is the time it takes for a moon to go from one full moon to another full moon, is 28.5 days, 29 days approximately. So if you take 12 of that, that would be 354 days. which is something like almost 11 days short of a normal solar year. That is a normal time period when seasons change. That's something approximately. So this would have been the first advent of a calendar, and this calendar was what we call as the beginning of astronomy and astrology in the Western world. So this calendar Hello, hello.
Hello.
Can you all hear
Yeah.
me?
Yeah, we can hear you
Yeah.
now.
Sorry. I mean, suddenly just the light went off over here, so my Wi-Fi switched off. I'm now using my mobile data. I suppose there should not be any problem. Okay. So let's continue. So till where were you all able to hear me?
The concept of a year but from moon.
Yeah. Okay. So I suppose you have not lost much. Okay. So well, this was the first advent of a calendar, and this calendar was what we call as the beginning of astronomy and astrology in the written form. Because by knowing that there's something in the heavenly bodies through which we are understanding season, people started putting more importance to this, and that is where lots of mythology started. Well, people just started saying then, oh, you know, this moon actually its position is not just telling us the seasons, but it is actually telling us lots more. And as we know, then all this different settings which are there telling us exactly what's happening, like the Kundali, which we have in India, or the zodiacs in other places came into being. So now I want to talk about this one thing, the flat Earth doctrine. So how many of you have heard of the flat Earth theory? So many of us say that the flat Earth theory is a hoax. It is something which people believe. But do you know that the flat Earth theory has its beginnings during ancient Mesopotamia? Yes, Mesopotamia, the civilization which existed something like 8,000, 10,000 years ago, because it's in 8,000 BC. 10,000 years ago, this civilization existed, and they were the ones who firstly proposed the flat Earth theory. That there's this very, very large plane, and it is sitting on the top of a turtle, and the turtle is moving about in space. Something like that. That was the first flat Earth theory. And we have to give credit to the ancient Mesopotamians for that. And although, I mean, I don't know if any of you are ancient Mesopotamians or Mesopotamians over here who believe this, but well, most of us do say that this is not true. I'm just trying to be politically correct over here by saying most, because there are some who might not agree with me. But we have to give them some credit because they were the ones who actually were thinking out that, okay, is there some pattern? Is there something more? So this image which you see over here, this is the oldest map. And this map, the circular part which you see over here, it is the circular flat earth. And there are three parts in the circular flat earth. There's Libya, there's Greece, and then there's the rest of Asia. And here it is written in Babylonian script describing exactly what it is. And this is from the 6th century BC. So this is a stone tablet which has survived for something like 2600 years. And this is the first tabulated form that we know of the earth. But we can't blame them because there were no one like Magellan and all those who had actually just traveled around the whole earth to see what exactly is there. So we can just look at this theory and we can be happy that yes, someone was trying to venture out. Okay, so flat Earth theory and circular Earth theory. I mean, they were wrong in saying that the Earth is flat, but still they were able to figure out that the Earth should be circular. Certainly, Earth is circular. I mean, this image of the Earth, if anyone looks at it, as long as they've not seen it from outside, they would feel like, yeah, it is like a circle. So why not a flat Earth? So, well, the thing is that their doctrine has existed for such a long time that you have to give them credit. Even the civilization that we are living in right now, the civilization which has got globalization, has not survived for as long as flat Earth theorists have. So, enough with the pun. Let's go to something else. So, how many of you have seen this novel? son of Neptune, Percy Jackson. How many of you have seen or read any of Riordan's novels? The Lightning Thief, Percy Jackson. There's a whole movie series. Some of you might have seen that, right? So I'm just trying to keep this over here so that you all know that even there's popular reference of Greek gods and Roman gods in the form of planets. And they had a huge say in what is currently known in astronomy. So let's just talk about the planets that we know of: Mercury, Venus, Earth, Mars, Jupiter, Uranus, Neptune. Out of these planets, which are the planets which are named on Greek or Roman gods? The answer is every planet other than Earth. Even Earth is called Gaia in many places, which would have been the Greek form. But otherwise, all other planets refer to some Greek or Roman god, and their equivalent Greek gods. So ancient Romans actually had a huge say towards how we have seen our universe. And they were the first one who categorically understood what we are seeing in the heavenly bodies. They actually were the ones who were the learned people. And their philosophers were the ones who have influenced astronomy, mathematics, physics for millennia. Okay, and most of the theories were not correct, but their advancements in observational physics actually helped us just look at the universe in a different picture. They were the ones who actually allowed us to look at things from a different perspective. Instead of following the norm, they were the ones who ventured out. They were the ones who actually wanted to question things. I'm not saying that all of their questions were asked correctly or answered correctly, but still the ability to ask questions and ponder over them and not just believe anything. That is the crux of things which the ancient Greeks and Romans had. So let's talk about a few of these ancient Greeks and Romans. The first one, Aristotle. So most of you who have had any course on science communication would have actually heard of Aristotle. He is one of the most famous disciples of Plato. So Plato is the same one who has given Platonic solids, and Plato is that one person who actually made the first clock. Yeah. So the first clock as we know it, or should I say the first alarm as we know it, came into existence due to Plato. And Aristotle was his prized student. He was a genius. He was a polymath. He actually knew about lots of things. But he, at that time, knowing what was around him, described a universe. He described an Earth-centered universe. See, you still have, I mean, people are still in that age where they feel like everything around them is made just for them. This earth exists for me. All these plants exist for me. They give fruit so that I can eat them. These animals live so that I can slaughter and eat them. This river is there so I get the water. The sun is there so that I can get the heat. This moon is there so that it looks beautiful. These stars are there so that I feel happy. This was the picture at that time. It was completely man at the center and everything around. And Aristotle was the one who put forward that theory in a more central picture. But not everyone believed that theory. So many people refused Aristotle's theory, but his theory remained for a very, very long time. Then I'd like to talk about this guy, Eratosthenes. So Eratosthenes is famous not just for his work in astronomy, but also because of his work in astronomy. So Steve of Eratosthenes is very famous in maths. If you ever want to figure out what are the primes in numbers, so Eratosthenes actually had developed this technique in which he says that, you know what, list out all the numbers, then choose the first number which is not a prime. So for us, it would be 2. And then cancel out all the multiples of 2. Then choose the next number which is remaining. Then cancel out all its multiples which are remaining. So the next number remaining would be 3. All its multiple would be, so next multiple would be 9, 15, and like that you're cancelling them all out. Next number remaining is 5. Cancel all possible multiples of 5. And like that, what would be remaining would be prime numbers. So that's the same of Eratosthenes. But that is not his major contribution. So Eratosthenes was the first person who was able to compute the circumference of Earth, and he computed it with a 1.4% accuracy. So people in NISER, You all have done experiments for finding out the acceleration due to gravity, right? I remember we used to have 4 different experiments for finding out acceleration due to gravity. And normally the error bar would be something between 4 to 5%. With the current technology that we had, we would get an error of 4 to 5%. This guy, Eratosthenes, in 300 BC, when he had access to nothing, he was able to figure out the circumference of Earth to an accuracy of 1.4%. Now that is goddamn amazing. And his technique was very ingenious. So what he had done was that he had said that, sun is so far away that the light from sun is coming to us almost in parallel. So there was this huge well which was there in sign, and what they'd done was that during the equinox, the vernal equinox, they actually saw that when the sun is exactly visible, so when sunlight is exactly visible on the bottom of the well, that is when sun is exactly on top. At that time, near Alexandria, they had a pole. So they measured what is the shadow length of that pole. So based on that, they were able to figure out this angle alpha. And just using some clever geometry, you can see that this alpha would be the angle of the arc subtended by this distance. So based on that, they were able to figure out that if we know this distance accurately between Sion and Alexandria, that would actually give us the distance, the circumference of whole Earth if we divide it by this angle alpha. And that is exactly how they were able to figure out the value of Earth's circumference in 300 BC. Now I challenge any one of you out there to calculate the circumference of Earth right now, if you possibly can, maybe in the next few days, with all the technology you have available. As long as you're not using Wikipedia or Google, it is very, very difficult to calculate that. Okay, so moving forward, now we have gone from BC to AD, and now we are in the timeline of Ptolemy. So Ptolemy is a very famous figure because he was the one who exactly told us how to make graphs, how to put meridians and all that. But he was a bigger, he actually was the one who promoted Aristotle's universe. So he promoted Aristotelian philosophy, as we'd like to say. And he built up on Aristotle's geocentric model. And at that time, he figured out exactly how the stars are moving about, the geometry and everything, how they're moving, in what path cycles the planets are moving. Now, take a break over here and imagine that we know sun is in the center and all the planets are revolving around the sun. At that time, they didn't know that. They were thinking that Earth is in the center and everything else is revolving around the Earth. But then they saw that these planets, they actually make loop sorts of patterns whenever they're moving about in the night sky, when you observe them for long enough. So at that time, Ptolemy was very much just boggled how to do that. So he had to develop a theory of epicycles, that planets are not moving in circles, but they're moving in something like a spirograph. So imagine a circle in which, so imagine a circle revolving around this, around our Earth, and in this circle, the planets are moving. So that is what you call as an epicycle. And that made computations very, very complicated. But still, Ptolemy persevered, and he was able to give exact computations of how to compute the positions of various astronomical objects. Quite something. Just to make up for all the errors they were getting, they actually had to do some extra computations. Hats off to this guy. Although he was wrong, but still, these were the people who were pioneers. Okay. Now we come to the ones that we all want to wait for. Indians, right? So tell me about that one Indian whom we relate to whenever we are talking about astronomy. You can switch off your mics and answer this one, please. Aryabhat. So this is Kumar Sanidhya Shukla. Aryabhat, exactly. So Aryabhat was the one person who started the whole movement for astronomy in India. There were people before Aryabhat as well who did some astronomy, but they were mostly doing it for Jyotishashastra. What we know is that during something like 12th century BC, Rig Ved had mentions of astronomy. And if any one of you is spiritual enough, you would have heard that our universe is nothing but a dream of Brahma. And then there are these different yogas which are there. Then there's this Mahayoga, and then there are these different cycles which are happening around, and then the age of the universe and all things like that. There are lots of people who preach that, although most of those things I don't know where they came from, but well, people had some idea that yes, there's something happening. But Aryabhat at that time was just out of the picture from everyone, because he just observed that solar eclipses are happening, lunar eclipses are happening, and the sun is moving about, moon is moving about, but how can that happen? So he was able to figure out that if you're in a boat, you would see that everything around you is moving. So it's not that everything else is moving, it's that you're moving. So Aryabhat at that time had proposed the heliocentric theory, and that heliocentric theory was something that was used by everyone. They were ready to believe that yes, it is a heliocentric theory, everything is moving about the sun. And using that theory, Aryabhat was able to give lots of different computations regarding how the earth is moving, what is the time when the sun would rise, the moon would rise, the different planets and everything. And he was very, very accurate. So accurate that even right now Aryabhat's text exists, and if you try to compute anything from Aryabhat's text, they hold till date. So that was quite something for someone who had no access to a telescope or anything like that. Just based on what they're observing, they were trying to interpolate the data which they had, and their interpolation was so precise that it holds till now. Okay, what more? So the another major aspect of our Indian astronomy was the Panchanga. So the Panchanga is basically Panch Ang, five different parts, and these five different parts exist for every heavenly body. So based on that, there are asterisms which we call as nakshatra. Then there's the different houses which we call as there's a proper Hindi name for that. I can't remember that. Sorry, but with this, they were able to again figure out the entering of a heavenly body in one thing and another. So there's the Shukla Paksh, there's the different Pakshas which are there. Then there are the different Vidhis which are there. So all of these are corresponding to the Panchangas. And again, these panchangas were something which were made based on what the ancient Indian astronomers had done, mostly work of Aryabhatta, and that has gone on till now. Okay, so this was the thing which happened till the 5th century. But what happened is that for a long time there was no progress. This whole period is called as a dark period, because in this time scale there were no new discoveries. I mean, see, as I said, our model of the universe is correlated to how much we understand astronomy, how much we understand physics. And what we understand about physics right now is just based on, at that time was just based on what they were seeing. But they couldn't see anything outside, and they couldn't conduct any sophisticated experiments for a very, very long time. So this dark period existed. And this existed for almost a millennia. For a millennia, there were no new discoveries. There was nothing which they could feel like, yeah, we have figured out some new part of the system. We have figured out some new rules of physics. No, they were just going about with whatever they were seeing. Practices as they had existed since the time of Aristotle and all that, they were progressing. And even till date, most people in most part of Europe were believing that, yes, Earth is in the center. So this was the time period when the Crusades were happening. This was the time period when Christianity was actually spreading out, Islamic religion was spreading out, and Christianity had this one motto where they said that. So I'm not trying to blame any religion over here. Don't mind me over there. But they were saying that God made this. God made humans in His own image, and Earth was made just for humans. Let there be light, and the universe was born. And God had made Earth just for mankind, and everything over there is just for humans to enjoy. The sun is there so that humans can get light, and that sort of a picture where everything is there for us to actually enjoy our lives. And this progressed for quite some time. And then there was something which was like a revolution, a scientific revolution. So there was a cultural revolution in most parts of Europe, which we call as the Renaissance. And similarly, there was a Renaissance which came up in science. And this Renaissance was spearheaded by the work of a few Western physicists and philosophers of that time. So this is the Renaissance in science. And this Renaissance is mostly appreciated by people who had seen how things were happening. But the Renaissance started with this guy, Nicholas Copernicus. So Nicholas Copernicus was the one who very fervently tried to say that, you know what, the model which I've been following for the past a millennia and a half about how the universe is actually centered around the earth and everything else is revolving around the earth is wrong. It is so wrong because the sun has to be at the center. Only then all these things which you're observing. See, now the time scale was where people were able to see things much nicely. And there have been a long time when, although there were wars, but people were still in much of a harmony. We were having records being kept from a long time. There was paper, there were other media of passing down information. So they had recorded lots of different phenomena. They may be comets, they may be other systems like eclipses and all that. By the way, Aristotle's model of a geocentric universe had been questioned again and again in this time period, but nothing in particular happened before the advent of Copernicus. So Copernicus formulated what we call as the Copernican heliocentric model. So the Copernican heliocentric model says that the sun is in the center of the universe. Our current model says there's no center for the universe. Whichever point you choose can be called a center, but there's no exact definable center for the universe. So Copernicus at that time just said that, sun is at the center of the universe, everything else is revolving around the sun. To an extent that is correct, because for the humans at that time period, only the sun and earth and the other planets would have mattered. The stars were just some blinking lights. But then things changed because of this guy, Tycho Brahe. So Tycho Brahe was a person of aristocracy, and this very nice story which is associated to Tycho Brahe. So Tycho Brahe, he was a polymath sort of a person, and he was associated in lots of things. But he was the royal astronomer for the Polish Academy, if I'm not wrong. And Tycho Brahe had not exactly gotten a telescope, but he had this, let's just say, something like a pinhole camera. Well, even a pinhole camera would be a wrong description. It was just a long tube which would have disallowed any light from outside to enter. And he could actually see in that long tube and keep on measuring the different right ascensions and declinations of heavenly bodies. And he made a complete data entry of these every day. But the story which Tycho Brahe has is that when he was young, something like in his 20s, he was quite a young, arrogant, being an aristocrat. So he got into a fight with another aristocrat who was his cousin, some of third cousin, fourth cousin. And during the fight, that cousin actually chopped off his nose. So Tycho Brahe would have brass nose that he would always keep on his face so that no one can see that his nose has been chopped off. But because his nose was chopped off, he could actually, so this is something which people credit to Tycho Brahe, that he could actually just take out his nose and put his eyes even closer to the aperture over there of this whole tube sort of a thing. And because of that, his readings were more accurate than all the other people who were his contemporaries. And what Tycho Brahe did is that he created lots of data, and the person who was able to use the data the most was his assistant, Johannes Kepler. So everyone has heard of Kepler's name. I don't need to talk a lot about Kepler. Johannes Kepler was a person who had done a lot, but mostly he took something like 20 years to go through all the data which Tycho Brahe had computed at that time. I mean, he had just written down, and by doing some back calculations, he tried to fit exactly what sort of an orbit would all these planets have. So at that time, they had almost abolished this whole theory that yes, the planets are moving about Earth. They had thought that yes, the heliocentric model should hold. But what Kepler found out is that instead of it being a circular orbit, it is actually an elliptical orbit. So the Kepler's laws of motion, or Kepler's laws for planetary motion, these are still there in physics textbooks, that if you have got heavenly bodies, they would be moving about in an elliptical orbit, and sun would be at one of the foci. Then there's the law which says that the time period is proportional, t cube is proportional to r square, and those sorts of things. So there are three laws of motion which Kepler gave. So these are things which can be derived by using Newton's rules. But before coming to Newton, we have to talk about a great person, Galileo Galilei. So he's so special that I would actually like to pronounce his full name. Galileo di Vincenzo Buonarroti di Galilei. I know if someone is from Italy, they would be cursing me for I have spelled his name wrongly, but still, he's such a great person that you should remember his first name. I mean, his whole name. So he was the most influential revolutionary. So he verified the heliocentric model. So people credit Galileo to making the telescope, which is wrong. He didn't make the telescope. Before him making the telescope, there already was something which was called as the looking glass, through which sailors would actually look at other things out there. Sailors would look at other sailors or things that are moving about far away. So there was already a thing like a binocular in existence. Galileo just had the idea of instead of looking down at things, he started looking up at things. And he looked at lots of heavenly bodies. He looked at stars, he looked at planets, and he specifically had a love for Jupiter. So Jupiter's moons are named by Galileo. They are also called as the Juno system. So there's Io, there's Ganymede, there's Callisto, and there's Europa. These four moons are the are the moons which, whenever, even if you have a very simple telescope, if you look through the telescope at Jupiter, you will be able to make out all these four moons. So it was quite fascinating because at that time people were still struggling whether the Earth is at the center or the Sun is at the center. Because even at that point of time, the church was not ready to accept that the Sun is at the center. They still wanted to have that special place. And Galileo at that time, I mean, he was in Italy, so Italy was a Christian state at that time, and his ideas were quite revolutionary, and people were ready to listen to Galileo. But his ideas being against the church actually created lots of friction. So he did lots of things. He was the first person who also observed the solar spots, but because of his adamance, because of his persistence towards saying the truth, he was kept in house arrest for the better half of his life. But one thing which you have to remember from this whole story is that he was the one who believed that he would rather face the whole world alone as long as he believes that the world is wrong. And this thing which he started actually created something that we'd like to call in Hindi akrosh in the scientific community, because his scientific views were based on facts. He was looking at things, he was observing things, and then he factually deducted things that this is how it should be. If you're considering the system of cycles and epicycles, which Ptolemy had done, then for us to understand what's around Jupiter, you'll actually have to make epicycles. That is, around Jupiter, again, there's a whole circle, and on that circle, things are moving about, and then you're looking at those things, which would have been too complicated. Instead, it would have been much more simpler to say that, you know what, there's some sort of a central force which is attracting everything towards the center. And we are moving about the sun, and everything else, like the moon and the satellites, they're moving about the planets. This was initially Galileo's idea, which was then later formalized by Newton. Not this Newton, but the Newton which Alexander Pope had told about. Nature and nature's laws lay hid in the night. God said, "Let Newton be," and all was light. So this poem is actually quite famous, not because of the poem itself, but because of it being getting mentioned in Dan Brown's novel. How many of you are Dan Brown's fan? Has any one of you ever seen any of Dan Brown's movies? I mean, there's the Da Vinci's Code, Angels and Demons, and things like that. A yes or no would suffice. So if you have seen Da Vinci's Code, then you would figure out that in Da Vinci's Code, there's this one part in which they say that, okay, who was the one, someone who a pope actually praised. So a pope over there was Alexander Pope. So was his, they were trying to just jumble out words, but it was Alexander Pope who had written this poem. And Pope being a Christian figurehead at that time period, no one would have expected a Pope writing something good about a scientist. So Alexander Pope was the person who wrote about Newton, and it has stayed with us for a long time. Sir Isaac Newton. Now we are in the 17th century, and do you feel that I should actually introduce this guy? I mean, I don't. He was the one man who actually just looked at all the physics which existed before him, and he just said that, you know what? Maybe I can just put all this together into a unified theory. And he came up with three very, very nice laws, which we call as the laws of mechanics, the laws of motion. For every action, there's an equal and opposite reaction. Force is the rate of change of momentum, and a body at rest would continue to stay at rest, or if is in motion, it would continue to stay in motion as long as there's no external force getting applied. So I have said all those laws in the opposite manner: the third law, first law, second law, and first law. But those were, I'll say, not his biggest contributions. His biggest contribution was the theory of gravity, and along with that, calculus. Okay, so let's proceed a bit towards telescopes. So after Galileo started looking at the night sky through his looking glass, which we call as a telescope, people started thinking about what can be done with telescopes. So people started with telescopes, very simple telescopes. So this is the telescope which Galileo used. They are in some museum in Italy. And as you can see, these are very, very primitive telescopes. Very, very primitive. I mean, there's a tube with one lens on one side and another lens on another side. And you can maybe just change the size over here a bit so that you can keep things in focus. Newton was a bit more ingenious. He was able to see that whenever you're having a telescope, as long as you're using lenses, there would be some chromatic aberration and even spherical aberrations. So Newton designed a telescope which was reflective. That is, it actually had a mirror. So this is the telescope which Newton originally used. It is there in the museum, Newton's museum. I suppose there is a specific museum for just Newton's work. This is there in that. That's what I could get from the net. But these are very small telescopes. The one that you have in NISER, the one which I remember, the Celestron Explorer that was there, that was an 8-inch telescope, 8-inch or 6-inch telescope. This was a 3-inch telescope. And through that, Newton was able to see lots of things and able to formulate the law of gravity. Okay. And then this was in the 1800s. This was William Herschel's 49-inch telescope. Okay, that's quite something in the 18th century. And what do we have right now? So this is the European extremely large telescope, which is having a 39-meter diameter mirror inside. With this telescope, if you try to look at the night sky, you would be able to see things which exist beyond what we call as the Virgo supercluster. So that is maybe a few billion light years away. That is how much we have progressed. And telescopes. So if anyone asks what is a telescope, the best answer is telescopes are time machines for astronomers. The better the telescope, the better a time machine it is, because the further away it can look in the future, I mean in the night sky, the further away it is looking in time. So the advent of these telescopes actually made people think about a lot of other things as well. Okay, we have got a night sky. We have actually got lots of things happening out there. We have got amazing pictures of stars, of planets, and then around these planets we are getting satellites. And people started observing things. And they were not just observing things; they actually started questioning things. Why are there stars happening? I mean, rotating about in some specific motion? So Newton had already given the answer, and this is a caricature of Newton and the apple. A very famous story which has been told to all of us, that Newton was sitting around reading something. People say that he was formulating calculus at that time, and an apple fell on top of his head. And then he started to question, why is apple falling down and not up? What is making it fall down? Is something compelling it downwards? And that was when gravity came in picture. Okay, so I take a short break over here. So any questions till now? I know it's mostly a story, but still, any questions? Okay. Guys, I'm audible to all of you, right? Hello.
Yes, Bhaiya, yes.
Okay.
Yes.
Okay, so then I'll continue. So Newton and the apple became a very famous story. Okay, but then things changed. things changed drastically. Now here we are having a big leap. And the big leap happened because of this one thing that we call as the perihelion of the precession of Mercury. So we know that planets, they have an elliptical orbit, an orbit which is moving about in an elliptical manner. But what happens is that these elliptical orbits, they keep on shifting. Okay, and this is what we call as a perihelion. And the precision over there is how so this perihelion is the closest point that we have in this whole orbit. So Mercury was having a precision, and Newton's gravity actually gave us a way of understanding this precision. But Newton's gravity was not giving us the perfect picture. To get the perfect picture, in the sense that Newton's gravity gave us an idea that yes, there should be some precision, but that precision was very different from the computation or the observations which were done at that time. So people started to question that maybe either our observations are wrong, or Newton's theory of gravity has got some flaws. So Newton's theory of gravity had been checked for larger distances, but at this small distance, there were some problems. And these problems are what we call as, this actually arrives. So currently we explain this by saying that there's something like a short radius behavior around this whole area of the sun, where the position of Mercury is getting changed, not because of the accountants of other planets and their attractive forces, but because of general relativity, because of the way gravity behaves around a very massive object. So now comes the time period of Einstein. So this was a satire based on the previous poem by Alexander Pope. So if we look at this poem, nature and laws lay hid in the night, God said let Newton be, and all was light. So this was a satirical poem. It could not last, the devil shouted ho, let Einstein be, restored the status quo. So this was a satirical poem by J.C. Squire, in which he does something what Alexander Pope does for Newton, but he says that now the error belongs to Einstein. And Einstein's theory of relativity is the one thing which is explaining things. So I don't need to tell much about this guy, Albert Einstein. I mean, this guy is equated to being a genius of unbound, let's just say, mental capability. I mean, he's not someone who can be compared to anyone. If someone asks me that is there anyone in existence who could be compared to Einstein for the amount of brain matter that he had in current times, maybe Ed Witten or someone like, well, if I'm coming to maths, there are guys, but in physics, I don't know if I can compare someone with Einstein. Einstein was just nature's gift to physics. He was able to see a flaw which came up in Newton's gravity, and he was able to correct that flaw. And that was not his only contribution. He was the one who pioneered quantum mechanics by his explanation of the photoelectric effect. He gave the special and general relativity, and this precision of Mercury that we are seeing over here can be explained to a very precise degree using general theory of, special theory of relativity explains this to quite an extent. And yeah, as I mentioned this, so general theory of relativity actually gives us the rules of nature, which govern nature all around us, in the sense that Newton's gravity is correct, but Newton's gravity comes out to be an approximation of Einstein's relativity at either a faraway distance or at low energies. So what I mean by these terms would be a bit technical, so I'll just keep it there. But it's not that Newton's theory of gravity was wrong, it's just that it was a bit of an approximation. It was not the complete picture. And I would not even say that Einstein's general relativity is the complete picture. But Einstein's general theory of relativity is the one theory which we feel should be able to explain most things which are there in the universe. Whether it is black holes, or whether it is quasars, or whether it is anything, alpha, beta, gamma out there in the universe, we feel that Einstein's theory of relativity would be able to give us a very precise picture of how it is happening. Because for understanding, as I said, that in science, what you need to know is to be able to predict things. Yes, we can make some observations and create a theory on that. But if the theory cannot predict something else, then the theory would not be that much useful. So Now just think back. I mean, we started from an era of early man. Then we came to the era of Greeks. Then there were the Indian astronomers. In between, there was this whole revolution which was created because of the advent of all these Western astronomers, Galileo and all that. And as science kept on progressing, we kept on getting a bigger and a better picture of the universe. So by the time of Newton, we understood that yes, they are planets, they are moving about, and there's this gravity which is keeping planets together. But still, that was all that we knew. Now, with Einstein coming in picture, we realized that there's something much, much bigger out there. So, as we understood relativity even better, we understood that yes, there are things out there which we can formulate, and they can actually explain things in a different manner. Okay, so let's proceed with this. Let's go to the Great Debate. So the Great Debate was something which happened during the 1920s. So the Great Debate happened between two guys. There was Harlow Shapley, and he had been studying what we call as globular clusters. And this is a distribution of globular clusters and how far away they are from the center of the galaxy. So he was looking at this, and he found out that these sort of globular clusters, they are having a very, they are very densely packed in this region, and then there's some globular clusters very far away. So Shapley argued that our universe is one big galaxy, which is something like 100,000 parsecs in diameter, and the solar system is quite far away from the center of this galaxy, and nebulae and the dust clouds and everything else, they're just a part of our galaxy. Okay, that was his argument. And then comes this guy, Herbert Curtis, and he argues that our universe is made up of lots of galaxies, some big, some small, and our galaxy is only something like 10,000 parsecs in diameter. And all these nebulas and star clusters, they are different, distinct galaxies. And this great debate was something which went on for almost 10 years. For 10 years, people never knew whether there are actually galaxies outside of a Milky Way. Mind you, I mean, right now we are living in an era where we can't see the Milky Way. But if you were living before the Industrial Revolution happened, before there were so much pollution that you would not be able to look at the night sky and see the Milky Way. So at that time, people would just look at the night sky and they could actually see the Milky Way. Even right now, if you're going to some place like Kerala, which is not having any light or anything like that, and there's no light pollution outside, there's no pollution also outside, you would be able to figure out Milky Way very, very clearly. I remember when we had shifted to Jatni campus, we were able to see Milky Way quite nicely for some time. But then as time went on, Milky Way kept on becoming fader and fader because industrial activities had started near Jatni as well. And that is one of the reasons why people had actually always asked that whenever you want to build an observatory, build it far away from the cities, build it far away from any place which has got pollution, and build it as high as possible. So there's no, aberration coming up because of clouds and dust and every other sorts of things which can actually create some sort of a disturbance in our observations. Okay, so enough with that. The thing is that we knew that there exists a galaxy which is containing lots of stars, which is our Milky Way. But is this all? So Herbert Curtis, without knowing, actually said that no, there should be more. Shapley said that no, these are all. I mean, our universe is this. The thing is, both of them were partially correct. Herbert Curtis was correct in saying that yes, there are many galaxies. We know that for a fact now. And Shapley was correct in saying that our solar system is very far away from the center of the galaxy. And the one who actually resolved this great debate was this one guy whose name almost everyone knows now, Edwin Hubble. I actually tried finding out different pictures of Hubble, but this guy actually has a knack for his cigar. No matter which picture I try to look at, he's always holding a cigar. There was one which I found out where he was not holding a cigar, but then I felt like, okay, this might not be in the best image. Let's put a cigar on his face. So enters Edwin Hubble. He's the father of modern astronomy, and at that time, he was the only one who had access to a 100-inch telescope. And then, using the 100-inch telescope, he captured images of Andromeda galaxy. And using Cepheid variables, he calculated the distance from our galaxy, from our Earth to the Andromeda galaxy. By the way, Cepheid variables is not a mathematical variable. Cepheid variable is a star. Most of you who are here have heard of Cepheid variables before, right? So Cepheid variables is something that we use for measuring distances, in a sense. So this is a photo of the Andromeda galaxy, which was taken after a long time. And this is the photo of the Andromeda galaxy in the photographic plate, which Hubble had taken. So this is 1923. Okay. And if you look at, so this is the region which Hubble had taken the picture. And what are our capabilities right now? So this small part of this galaxy, the Hubble Space Telescope has taken this big an image of that. And we can see how densely it is packed with stars. So this is how much we have progressed. So Edwin Hubble was able to resolve this whole great debate which was there. He said that, yes, you know what, both of you are correct. Our Milky Way is not the only galaxy. There are billions and billions of other galaxies. And our solar system is not in the center of the Milky Way. It is quite at one of the far ends of the Milky Way. It is between the Sagittarius arm and the this Aries arm, right? But he did more than that. He actually did observations on lots of galaxies, and he figured out that most of these galaxies, they are redshifted. That is, they are going away from us. And the farther away they are from us, the faster away they're moving away from us. And this is what we call as the Hubble's law. So he actually pointed out what are the different, he looked at different galaxies, then using the method of Cepheid variables, he was able to see how far away they are. And then he plotted the redshift so that he was able to get the velocities. And with that, he was able to see that the farther away they are from us, the faster away they are moving. And the gradient of this graph, this slope, is called the Hubble constant. Okay, so we have learned a lot about our universe. We have learned that our universe is quite big. Our universe has actually got lots of stars, and these stars are making up galaxies, and our galaxy is one of the many galaxies which exist out there. But what more happened? So what more happened is that people tried to figure out a unified theory, how this universe came into being. So this is a picture which is shown a lot whenever we talk about the Big Bang. So the Big Bang, or I should say the Big Bang model, is a cosmological model of our universe. How our universe came into being. What is our universe? So we are currently over here in this region where the fight between matter and dark matter has ended, and the galaxies are now getting away from each other. And this is a 13.7 billion year time scale. So if this was a 50 billion time scale, then we would have actually put in a heat death also in this. So that is what we say, that after some time, after all the stars have actually used up all the energies, after all the black holes have sucked up everything that they can, then the universe would actually start decomposing, in the sense that there would be no other source of heat left. Every source of heat would die down. All the white dwarfs have actually gone away. All the brown dwarfs don't have any geothermal activity. And the black holes have now started shrinking because they don't have anything, and they're completely shrunk out. And that would be the heat death of our universe. That is what the Big Bang theory model proposes. So mind you, this is a current model of the universe. This is not the model of the universe. This is just a model of the universe. We have got many other models of the universe. So these models of the universe, they are based on the type of physical theory that you are working with. So the Big Bang theory of a universe is based on two contradictory theories, which is general relativity and quantum mechanics. So this part, which we call as the Big Bang followed by the inflation, is something where our classical physics fails. We know that we have four fundamental forces, namely the gravity, the force of gravity, the electromagnetism force, then there is weak nuclear and strong nuclear. We don't know what was there before. I mean, whether these four forces were still in existence in this inflation and quantum fluctuation time period. So understanding the Big Bang, or understanding this model of the universe, requires us to have a unified theory, such that both quantum mechanics and special relativity actually match with each other, which right now is not happening. Our current understanding of quantum mechanics and special relativity are contradictory to each other. The one point where they do seem to match would be Hawking's theory of black hole, Hawking radiations. Okay, so this time period is actually very nice. We actually don't have much idea about the dark ages. We can't see anything from the dark ages. We can see some things from this era, but mostly what we can actually see is this. So this greenish bluish part which you can see here, the face of the baby universe. This is the cosmic microwave background, and this is what we like to call as the selfie of the baby universe. So why is this a selfie? Because the universe gave us the picture itself. So initially this was very hot, and it should not have been in the microwave background, but because of getting redshifted, it is. I mean, the frequencies are at least they say that it is 1100 times less than what they should have been. So they could have actually gone to something like the ultraviolets, if not anything else, if the redshift had not happened. But because of this expansion, there was a huge redshift, and the redshift was something, as I said, 1100 times. And that is what made this all come into the microwave background. I mean, as a microwave background. So this microwave is the same microwave that we have in our homes, but this microwave is, I mean, this whole background image is something which took close to 12 years. There were 3 major satellites. There was Kobe, there was WMAP, and there was Planck. These 3 were able to map out all the microwave background which is there, and they were able to see that this microwave background exists in the night sky. This microwave background exists, and this microwave background is a perfect Planck black body radiation background. It exists at a temperature of 2.7 Kelvin, which says that the temperature of our universe should be around 2.7 kelvins, the average temperature. So 2.7 kelvins, it's just a number if I'm saying it, but liquid nitrogen becomes a liquid at 73 kelvins. Okay, so again, we are now trying to proceed forward with what we know right now. So this is the Hubble Space Telescope. Everyone has seen that. Some of you might have actually even tried to look at it through your telescopes. And it is one of the biggest projects which NASA started. And this has actually given us some of the clearest pictures of our universe. But what Hubble Space Telescope did was something just amazing. So you see this image over here. So this was for the Hubble Deep Field. So Hubble Deep Field is a very, very small part of our universe, of the night sky, where it actually just concentratedly took images for a few years. So this whole image is 1 degree by 1 degree. So our night sky would be made up of 360 degrees, okay? And this whole image is of 1 degree. So just for reference, moon would be half a degree. So a quarter of this image can be covered by moon, okay? And this image is just above Ursa Major, what we call a Saptarishi. And we have chosen this part over there. So you can see this sort of a block over here, this yellow block. This block is where Hubble focusedly took lots of images. What do I mean by a lot? It took close to 7,500 images of this small part with long exposures and all throughout lots of time. So it could actually get a 3D picture. Okay, by using different techniques of Seifert variables or maybe Hubble's law, they were able to get a 3D picture. So next image is gonna just be a magnification of this by the Hubble Space Telescope. So you saw that sort of a block. This is that same block, and this block covers almost 1 by 24th million of the total area of the night sky. And in this 1 by 24th million of the total area of night sky, there are more than 3,000 galaxies. And that is what all we can see. There's also something called as Hubble Ultra Deep Space, where they are trying to look at even smaller parts. And what this just goes to show and prove is the principle of homogeneity and isotropy. That the universe is homogeneous and isotropic no matter where you look at it. By the way, the choice of this part over here was based on lots of things. So for deep field, they actually had to choose some part which is not lying anywhere where the Milky Way's arms are extending. It has to lie away from any of the major galaxies, any of the major dust clouds, any of the major nebula. So this has to be in some place which is just directly pointing at a blank part of the universe. So these galaxies, if you look at them, only the very close by ones, only the very bright ones might appear like they are a bit spheric. They're a bit like spiral galaxies. Most of these galaxies, they actually look like elliptical. And this goes to just tell us that, when the universe evolved, the first galaxies which came into being were elliptical, and then the elliptical galaxies evolved by becoming either spiral or barred spiral, and that's how it proceeded. Okay, what more? So as I said, we have got a picture of the black hole now. This was by the Event Horizon Telescope, which was a culmination of not just one telescope, but a lot of telescopes. So here's the question. Is this it? Is this the complete picture of the universe? That is not even close to what we can say about the universe. Our universe is so big that we don't know whether some of the phenomenon which we have verified over here might hold someplace else. We don't know what sorts of physics would actually hold inside a star. We don't know what sort of physics would actually hold inside our own Earth. We have not gone that deep below. We have just seen things by making some observations, and we are trying to extrapolate those observations. The good thing is that these observations hold. The good thing that we have been able to realize is that general relativity holds. But does that mean general relativity is the correct theory of the universe? We don't know. Maybe we need a theory of quantum gravity or M theory or who knows what else. I don't for certain. But all I can say is that it's a fun process to go about through this. So I'd like to recite a poem which I had learned long back. Physics is a game. Physicists are the players. The rule of the game is to find a new law of nature. You gain a point by finding a new law of nature. The game is never over because no one can win this game and it goes on forever and ever. Okay, that's all, folks. Thanks for listening to me boring you all. And now, please ask away questions. Yeah. So, okay. So there's this question: can we say that the universe is in its beginning age, or it has aged more than half its possible age? We don't know. Quite frankly, we don't know. We have got no clue whether this is the beginning part of the universe or the ending part of the universe, or the universe would just stay constantly like this. What we do know is that because the galaxies are getting redshifted, that means that at some point of time they were actually going away from, so they're going away from each other. So they're going away from some center. So if we try to just back compute based on that, okay, based on this, how far away they are and how much distance they have covered to get it shifted that much, we try to back compute, we can say that yes, they should come out a point where it all started somewhere. Although saying that Big Bang was a point would be wrong. I mean, it's a singularity, but that singularity was there in all of space-time. So it started at some point of time, but we don't know whether the universe would evolve to, whether this is the half age, whether this is 1/4 of an age, or whether the universe might end tomorrow. We can't say that with guarantee. The current model that we believe to be true is the Big Bang model based on standard theory of particle physics and general relativity. That says that our universe would have a heat death somewhere close to 50 billion years. Okay. So there's this other question. Before starting of the talk, the speaker mentioned something like, is a geodesic if we take time as a parameter? What was that? I'm not asking what is a geodesic, I'm asking what was that physical quantity he was talking about mentioning geodesics? Okay, so the physical quantity which I was mentioning was that if you're considering a universe as a space, a universe as things in space-time, and everything in space-time is getting created by the different, so I can consider my universe as a manifold. Manifold would be something which is not, locally Euclidean, locally which you can actually see as just flat. And then in this manifold, it can have different say genuses. So any sort of a singularity is just tearing up this manifold. That is what we will call as a black hole. And by saying that we are going forward in this manifold, or by saying that time is moving forward, I'm saying that we are having a parameterization of space-time in time. So we are just a geodesic in that sense. The other question is, if the universe is space or any other Euclidean space, how do you well define the center of it? We can't. We just can't. So to define the center of a space, firstly, you need to say that it is bounded. It is like asking, can you say that there's a center of real numbers? The answer is no. No matter which number you choose, that's the center. So wherever you're starting can be the center, wherever someone else is starting can be the center. There can be no definite center as long as you're considering your universe to be infinite. If you're considering the universe to be finite, then well, yes, it is possible to define a center. Okay. Any other questions? Satyam, you're there? Hello? I can't hear anyone. Hello?
Uh, yeah, yeah, you are audible.
Yeah, okay. So I suppose I have not done justice to this topic by trying to just rush forward with things. But
Yeah, the storytelling format that you mentioned and you went through was interesting, and I think and there aren't many talks on this format.
I actually wanted it to be in my spirit of popular science talk. See, didn't want this talk to be all mathematical and physics. Oh, we have got questions. Okay, so when we take parameterization, the domain must be an interval on R, but is time continuous in nature to be a parameter? Uh, so that is a very fundamental question, Achasman. And I would rather say that you can actually ponder about that question a lot. Is time a continuous parameter? Is it discrete? If you're going to quantum mechanics, nothing is continuous. If you're going to relativity, everything has to be continuous. That is where the fundamental contradiction lies. So we can't answer that question as of yet. You need something like a unified law, a unified theory, which again is a big dilemma for us because there's a bigger mathematical theory which says that you cannot have a unified theory. So we cannot exactly say which would be the answer towards our universe. Okay, can you explain more about how the telescopes are time machines? Whenever you're looking at any point in the night sky through a telescope, you're actually looking at the light which came from that star, okay, or from that heavenly object, or from that object in the night sky. So if you look at the images taken by Hubble Space Telescope, they would say that, okay, this is so many light years away. So let's just say something is 3 light years away. That means it took light 3 years to take from that planet to come over here. As an analogy, let me just say that there's someone who's actually in Alpha Centauri, which is something like 5 light years away from us, in some planet around Alpha Centauri, and he sends your message through a radio communication. So it would take that radio communication 5 years to reach you. So once you receive it, you will feel like you received it now, but it took 5 years for it to go from there. So similarly, if you are looking at some different let's just say if I'm looking at Andromeda, it's something like a few what it's something like a million light years or something like that. I mean, some x number of light years away from us. And if you're looking at that picture of the Andromeda, it is something like you're looking that much back in the past. If you're looking at any of the galaxies which were like 10 billion light years away from you, you're looking at their images that they were showing 10 billion years ago. That is why they're called as time machines for astronomers. Okay, so there's another question. Doesn't the fact that there's no center of the universe challenge Olber's paradox? So Olber's paradox normally just says that if there's so many stars, then the night sky should be bright, right? But now, one of the very nice ways through which Olber's paradox was resolved was by this poet. I don't remember his name, but he was a philosopher and a poet, and he had actually argued simply by saying that if you are considering light to be having a finite speed, and these are not that densely packed, then you can actually figure out that yes, it would not be so bright. So I don't think so that this would in any way challenge the Olber's paradox. Chandan, does that answer your question? Okay. Yeah. So any other questions? Well, most of you are from NISER or from some other research institute, so I'd just like to say it over here that the universe is fascinating. The universe is something which people have been trying to understand for time immemorial, and we still don't have a proper picture. And people would be working on getting a unified theory for a very, very long time. But just keep a spark in your mind. Just keep a spark in your mind that no, maybe just a small contribution from us might take mankind a few steps ahead. Einstein's understanding of relativity actually took mankind so far ahead from what we understood of the universe that right now, every technology that you have in existence, whether it is a smartphone or the laptop with which you are looking at this, or maybe the tablet through which you are accessing internet, all of those are based on lots of technology which you can use right now because of relativity. The mobile communication which is happening, those communications getting transmitted through satellites getting their corrections because of relativistic corrections, all of that is being made possible because of special and general relativity. And these were nothing but some mathematical formalisms to explain how things are happening in the universe. So these are very small steps for humans, but large leaps for mankind at times. Okay, how far relativity and quantum mechanics have gone towards unification? Not far. That's why we have got many other different unified theories. So there's the grand unified theory which people want to work with, but there's also quantum gravity. Then there's the bosonic field theory. Then there is this lambda CMD theory. Then there's M theory. There's string theory. All of these, the major idea is just to be able to unify all of physics that we know. So Einstein at that time was just trying to unify general relativity with quantum mechanics, sort of a thing. So he had tried. I mean, general relativity does try to unify electromagnetism and gravity, but Einstein at the time didn't focus a lot on strong and weak nuclear forces. String theory, M theory, lambda CMD, all of these do focus on all the four fundamental forces, and they're trying to figure out if it is possible to unify all these four fundamental forces. But there's still major questions that we haven't answered. Right now, we have got no idea what is dark matter, what is dark energy, although we know that they exist. We know that there exists dark matter because the way our galaxy is spinning. The spin cannot be explained without the presence of some matter which is not getting accounted for no matter how much we have studied. The accelerated expansion of the universe is expanding true, but there's an accelerated expansion which can only be explained by saying that there's some sort of a thing which is getting pumped in, which is dark energy, and that is giving us the accelerated expansion. Can we explain that? Hell no, we have got no idea. These are still open problems, and for that we actually need a big leap in our understanding of physics. By the way, I am actually a supporter of just saying that a unified theory cannot exist. Because if, so there's this thing called as Gödel's incompleteness theorem, which says that if you have got a mathematical system which is robust enough, that is, it can allow you basic arithmetical functions, then there will always exist some of the other thing which you can neither prove nor disprove. So similarly with our model of the universe, our model of physics, whatever we learn in physics, we are just trying to model. We're just trying to put a mathematical model over there. It's like saying that if I have a ball, if I throw it, it would go in projectile motion. That seems to be true, but once I say that it's a plastic ball and I'm spinning it and then there's lots of wind moving about, you'll have to put in consideration that yes, there's some viscous drag, there's some sort of a Magnus effect happening, and then there's the whole curvature of the ball, how it is moving about. So you keep on adding second order, third order, fourth order corrections to your theories. So similarly, the theory that we have right now, they are just some first order theories. We need to have even better theories. And there was this sort of a statement by a physicist, I don't remember his name. He said that the theories of physics, they are like the peels of an onion, but the onion has infinitely many peels. Okay, I suppose I have talked a lot and I have bored you all also a lot. So Akshay, would it be okay to end it over here? I suppose there are no more questions.
Yeah. Are there any other questions? I think there aren't many questions remaining. If you still have any questions, you can send them to me or in the link provided in the invitation email. That is the email of Sagar bhaiya. So
you can just
since
send
there
me a mail.
aren't any other questions.
Yeah, please continue. Sorry.
Yeah, so since there aren't any more questions, thank you, Sagar bhaiya.
Thank you, all of you, for coming and listening to me. Thank you, Akshay, and on the whole of NISER Astronomy Club for giving me this opportunity to speak over here. I hope you all were able to enjoy this leisurely talk. And I'd be very happy if any of you have any questions, just hit me up on my mail. Thank you.
Okay. Thank you, everyone. Take care.
Okay. Stay safe, everyone. Bye-bye.